In this problem, we have this frame, and this frame has two members. It has members AC and members CB. It is also being subjected to a 500-pound force, a 200-pound force, and these are at some angle, and a 4,000 foot-pound moment. What we are asked to do is we are asked to determine the components of the reactions at the supports A and B. Now, A is a fixed support, B is a roller. We are also told a couple of other things. First, we can neglect the thickness of this beam. That's going to simplify our analysis when we deal with forces that are in the x direction because they're all going to lie on the same plane. The other thing we are told is that point C right here connects AB and CB by a pin force. And that's going to be important when we draw our free body diagrams. Now, the method we're going to go over will work for any frame problem or machine problem that you have. So let's start by drawing the free body diagrams of our individual members. When we are drawing these free body diagrams, we want to be on the lookout for any points that are shared between the two members, such as point C, that pin joint, or any two force members that we can see. Two force members will greatly simplify our analysis in the work that we are going to do. Unfortunately, this problem does not have any two force members. So I just want to write up here, one, we want to look for two force members. And two, we want to identify common points, such as pins. All right, so first I want to draw in my external forces. So my external force is going to be this 500-pound force, and it makes an angle by a triangle, and this is 5, and oops, this got lost, but that's a 12. This is a 12. So a 5, 12, 13 triangle. And then here we're given a 200-pound force. And this angle right here is 60 degrees. So those are the external forces. We have an external moment, this 4,000 foot-pound force that's in the clockwise direction. Now we need to take care of our reactions. So at B, we have a force that goes up. It's a roller. So B is going to just be a By. At A, this is a fixed reaction. So we're going to have some force in the X. We're going to have some force in the Y. And the one everyone always forgets is we're going to have some moment reaction force. Now, if we had any two force members, we would draw those. But then we need to take into account common forces. And we need to see that point C is common on both of these free body diagrams. So this point C is the same as this point C. What that means is when we identify these internal forces, our first time we see it, it could be either or. I'm choosing the member AC. We have a free choice on how we set its reaction, its internal forces. So it's a pin joint. It's going to have a force in the X and a force in the Y. When we see it the second time, we no longer have that free choice, and it needs to be opposite of what we had originally chosen. So these forces CX and these forces CY, if you see, they're equal and opposite. But it's really important that we see they're the same because we're eventually going to link our problem together with these forces. Okay, so we've identified all of the common forces on our two members. And the next thing we need to do is we need to use our equations of equilibrium for each of our free body diagrams. As you get more comfortable with these problems, you could probably skip around a little bit and you can see that this is going to be the easier member to work with first. But when you're starting out, as long as you stay disciplined and you stay organized, you'll still get the same answer. It just might not be as direct. So I'm gonna just start out by using this member AC and using the sum of the forces in the x is equal to 0. In this force, I have AX, or in this equation, I have AX from right here. I'm going to have minus 500 times this 5 over 13. Now this is this X component of this 500-pound force. And because this thickness is negligible, they all act on the same plane. It's not super important for this equation, but it will become important later. And then we have this plus CX. And this is equal to 0. Next, we have the sum of the forces in the Y are equal to 0. And we'll have AY. We'll have minus 500 times 12 over 13. And then plus CY. So CY, this negative component of the 500-pound force, and plus AY. And this is equal to 0. So again, we can't really do anything with that equation. And the last equation I'm going to use, I'm going to do the sum of the moments about A is equal to 0. So AX, AY go through point A. Well, I can't forget my moment. So my moment A. And the X, this is why the thickness being negligible is important. The X component of the 500-pound force and this X component of CX all lie on that same line. So they all actually go through point A. So the X components are not going to exert a moment about point A. Only the Y component will. The Y component is going to be, it's going to be down like this. Oops. So my Y component, it's going to rotate tail first. So it's going to be minus 500 times 12 over 13 times the distance, which is 4. Now, a real common mistake I see all the time when I am working with components that are not just in the X or the Y direction is one of these two, normally the distance, sort of just gets lost. I don't really know why. Probably maybe you look at this and you say, oh, this is my force and this is my distance, but that's not true. This is really the component of my force and this is my component of distance. So just be careful. And when you're doing breaking up a force into components for a moment, that you have the actual force and distance. Okay, so we have this force right here. And the last thing we need is this CY force. CY is going to go head first. So it's going to be plus CY times this entire distance, which is 8. And this is equal to 0. Okay. So really can't solve anything with these set of equations. We have 5 unknowns. We have 3 equations. So we move on to member CB. And we have the same set of equilibrium equations. So the first one is the sum of the forces in the X are equal to 0. I'll have minus CX. I'll have plus 200 times the cosine of 60 is equal to 0. That's this force right here. And this gets me CX is going to be equal to 100 pounds. I'm going to star this because this is important. That's telling me that this force right here is equal to 100 pounds. This force right here is equal to 100 pounds. So see how we're starting to link them together. Okay, so now we use the sum of the forces in the Y are equal to 0. We're going to have minus CY. We're going to have minus, not 60, 200 times the sine of 60. That's the Y component of this force. And then we're going to have plus BY is equal to 0. Now, what point do we take a moment about? Well, we can take it about C or we can take it about B. It doesn't matter. In this case, whether we do B, we're going to get whatever CY is. If we take it about C, we're going to get what BY is. And then this equation is going to give us the other one. So it ultimately doesn't matter. I'm going to take the sum of my moments about point B, and this is going to be equal to 0. I got to remember my 4,000 pound force. So I'm going to have, this is going clockwise. I like to say counterclockwise is positive. So I'm going to have minus 4,000. Now remember this 200 pound force, the X component goes along, the thickness is negligible. So the X component goes through point B. So we only have a Y component. Y component is pointing down. As we rotate it, we're going to go head first. So plus 200 times the sine of 60 times, what's this distance? This distance is 4. And then we have plus cy times the total distance, which is 8 plus 4. So this is 12. And this is equal to 0. Now we can solve this equation for what cy is equal to. So minus 4,000, plus 200 sine of 60 times 4, bring it to the other side of the equation, divided by 12, and we get cy is equal to 276 pounds. So that's cy right here. This is equal to 276. And this cy is also equal to 276. Now I can plug this into the equation I have here. So minus 276 minus 200 times the sine of 60 plus by is equal to 0. Solve for by. So minus 276 minus 200 sine of 60 times minus 1, and I get by is equal to 449 pounds. And this is a positive, so we know that this is going up. Now, what we can do is we can go back to all of my equations over here, and we can start to use what we found from Cx and Cy. So Cx we know is 100 pounds. So we have Ax minus 500 times 5 over 13 plus 100 is equal to 0. Let's solve this for Ax. And we get Ax is equal to 92.3 pounds. All right, we'll figure out what AY is. So AY is going to be this minus 500 times 12 over 13 plus what's AY? 276. That's equal to 0. Bring it to the other side. Nope, I forgot the minus. Bring it to the other side. And we get that AY is equal to 186 pounds. So AY is, this is positive, so we know what direction that these are pointing. And then we just need to figure out what our moment is. Let me move this down just a bit. So my moment of A is the minus 500 times 12 over 13 times 4 plus this 276 times 8. So we can multiply that by a minus 1 to bring it to the other side, and we get my moment about A is going to be equal to minus 361.8 foot-pounds. This minus sign right here just means that this is actually rotating in the clockwise direction. So this is equal to 361.8 foot-pounds in the clockwise direction. So these are your answers. This, AX, AY, the moment about A, and BY.